Hello, physics students. So let's take a look at how physics and technology go together. Alright, so we're going to go through characteristics and behaviors of light, talk about the connection between physics and technology, and talk about digital images too. Alright, here's the assessment questions you'll see again at the end. Here's the physics terms. We'll talk about quantitative, qualitative, engineering, technology, pixel, RGB, additive primary colors, subtractive primary colors, rods and cones. So let's go. Alright, so the language of physics, we're going to use a lot of mathematics in describing physical phenomena. And it is very important for the science of physics that the world can be modeled with mathematical relationships. And in your common experience, you may feel like you've learned mathematical relationships before you learned physical relationships in this class, but the reality is that most mathematics, if really probably all mathematics, was developed to model things that happen in the physical world. Alright, so just a relationship here. So an English statement of this equation might say the speed is the distance traveled divided by the time taken, whereas the equation would be v equals d divided by t. Alright, and just to give you some comparisons here, so in a math class, you might have said, 6 equals 3 times 2, whereas in a physics class, we're going to replace those pure numbers with quantities or measurements or values, and values or quantities or measurements are going to have units unless they're ratios. So it is important for you to understand that when you see units after numbers, those are to identify the amount of something so that you can compare them with some kind of external standard. Because over here we could simply ask the question, well, 3 what and 2 what and 6 what? Alright, variables will exist in both your math class and your physics class. Usually in physics we assign a letter to the variable to help us identify what quantity is being related by that variable. So F for force, M for mass, A for acceleration. Sometimes the variables make sense and sometimes you'll be like, where'd you get that from? Alright, so equations let us write in quantitative numerical terms rather than just qualitative language. A qualitative interpretation of this equation might be that if you increase the acceleration, then an increased force would be needed to cause that increased acceleration. Alright, so you can go to your textbook and do this. Click the math icon to see examples of math concepts matched with physics applications. Now let's talk about engineering for a moment. So in engineering we're going to apply science to design products or inventions to meet human needs. That is a consistent need, and that is something that has historically been very well accomplished by engineers in the United States in particular. Alright, so engineers are going to invent technologies that are using scientific principles to perform a certain task. Alright, and just to look at the design cycle, so start with some kind of concept, design it, build a prototype, test it, evaluate the testing results, perhaps revise the prototype, try again. You may get stuck on this spinny wheel here for a while until you get a prototype that can be exported as a new technology that can be mass produced and sold at a profit. You may also notice that this cycle continues even after a product is brought to market, because you know, Galaxy S7, Galaxy S8, and so on, and they continue producing better designs, but with each of those there will still be this cyclic process. Alright, so iterative, in other words, is going to continue repeating iterations until an acceptable design is found. Alright, so technology, everything built in the human constructed world. And so looking at some technological things and where it fits in with physics, so communication, maybe electromagnetic waves, display, so optics and diodes, and how does that touch screen work, and why doesn't it work when it's wet? Questions like that. Processor and memory and semiconductors, battery, electrons, atoms. That's getting into the chemistry department a little bit. And then the case, maybe force, strength, and mass might be some things that you consider there. Alright, so one of the things that you can look at in the text and play with is how an image is captured and stored in a digital camera, how the colors are rendered. Alright, so digital image in a way is a trick, because the colors are in a pixel on a screen are actually just red, green, and blue, but by varying the amounts of red, green, and blue in each pixel, you can trick the brain into seeing a lot of different colors. And this additive color thing, and demonstrated this in class, and may demonstrate it again this week, but as you combine colors together, you can probably find videos on YouTube of this happening too. But maybe some kind of surprising results when you're combining light. This is not combining pigments. We'll talk about subtractive colors in a moment with pigments. Alright, so things that use those, pretty much everything that's got a screen on it is going to use that in the pixel technology. And within each pixel, it's going to have the ability to render red, green, and blue light. Alright, so there's a simulation in your book where you can play with this, but basically there's increments from 0 to 255 corresponding to the intensity of light for the red, green, and blue colors. And something wild for you to think about is that a 1 megapixel digital camera is going to be a string of 3 million numbers that tell the intensity of red, green, and blue for each pixel. And then, a lot of new cameras or new phones have cameras that are up in the 20-ish megapixel range. Alright, so go play with this interactive simulation, try it out, maybe try some color matches, make some colors, and you get to score yourself there. That's fun too. Alright. Alright, so there's a couple of different methods for creating colors. And this might be why sometimes, you're like, gosh, that color I see on my screen doesn't really match up very well with how it prints out. And some of that may be the printer quality, but some of that is there's some difficulty in changing between emitted light for producing a color and reflected light. So that comes about in a subtractive process. So this diagram shows you how the overlap happens. In a color laser printer, for example, you're going to have yellow, cyan, and magenta toners, and by combining those in varying amounts, you can make a variety of colors, as you see here. And this may be what you're a little bit closer to what you're comfortable with primary colors, mixing paint and things of that nature. All right, so when you view a color page, you're seeing the colors that are being reflected by that page. So that means other colors are having to be absorbed. So the cyan, the magenta, and the yellow pigments are used to absorb those colors, and you're basically seeing whatever's left to be reflected. All right, and something that's neat here is you can see the magenta, the yellow, and the cyan coming from those overlaps, which is neat, and then the red, green, and blue from the overlaps here in the subtractive processes. All right, so just thinking about things, light and color. So white light contains wavelengths from our perspective or interpretation. White light actually contains all colors of light, and you can pass that through a prism, which causes the light to refract and separates them based on wavelength from red to blue. All right, you might see a rainbow, and that's because the refraction is happening by raindrops instead of a prism. All right, so when we sense color, it comes about from the amount of light that we're receiving from a particular source and the different colors of light within that. So if we are perceiving something that's a mixture of red and green, then we're probably going to see yellow, and that's without a lot of blue light in it. So look at kind of the how of that. So we have rods that are detecting how strong or the intensity of the light, like how bright, and then the cones, which are picking up on the color, and these are located on our retina on the back of our eye, and that's what gets damaged, if you're exposed to a light source that's too intense or something like that. So in the cones, they have blue receptors, green receptors, and red receptors, and so certain people are colorblind because they're missing some combination of those cones. All right, so yeah, a digital camera, each pixel, I think we've already talked about that, but it has tiny red, green, and blue sensors, and then that data is saved and put on a screen, and the pixels will show those red, green, and blue in the varying amounts indicated by the file that comes from taking the picture. All right, so how can you see ordinary non-luminous, non-illuminated objects in the classroom? So they absorb or reflect, and the colors we see are the ones that are reflected. All right, what are those colors of light? Maybe pause the video and take a minute to think about it. And here are the answers. All right, technologies that use an RGB color display. I bet you can think of several. Here they are. And how the eye combines colors to see. And there you go. So that's the end of this presentation. Thanks for watching.